Hey everyone, I'm going to show you how to graph a derivative on your calculator. So we have this cubic here, and just looking at it, we can tell a few things about it right away, like the fact that when x is -1, the slope here is 0. So like if I were plotting points, I would plot a 0 right there. When x is 3, it's also a 0 slope, so I could plot a 0 right there. And then in between, I have these negative slopes, so I would be below the x-axis. But we can have our calculator do all of this for us. And here's how this works. So in our y equals screen, we have in my y1 is the original function. I know it's a really gross equation. I wanted a tidy graph, and that's what I ended up with. Okay, I'm going to go down to y4. I could put this anywhere. I like having it lower, and then I'll just turn it on and off, and I actually just leave it in that y4 line. And I'll show you how to turn it off and on in a second. So to make the derivative graph happen, we push the button called Math. And looking at this list, there's something called n-deriv. And this is called a numerical derivative. You know those difference quotients we were talking about? It's doing symmetric difference quotients and plotting points. So when it draws it, it's really slow. But it's called a numerical derivative. Our book will call it, find a graph or find a derivative numerically, which really means find a derivative calculatorly, but that's not actually a word. So anyway, I'm going to go to 8. So I have this n-deriv showing up. I'm going to show this twice actually. This is what it will look like if you have a Ti84. You'll see the words n-deriv show up. If you have a Ti84, it looks a little different. I'll show that in a moment. And then to get the y1 to show up, which is what we need, on a Ti83 it's vars, and then we arrow to yvars function y1. And then the format on this, and this is for the Ti83, we do a comma, which is above the 7, and then an x, another comma, and an x, and a parenthesis. If you have a newer calculator, it will look like this. You'll see d over dx, don't worry about that notation yet, and you actually end up typing that little x in there. You'll see an empty box when you pull it up. You put the y1 in there with alpha trace, and then you put the x at the end. So actually, I'm going to go ahead and do that. So math 8 gets the n-deriv, and I put an x here. I put my y1 using alpha trace and an x. So I've showed you two ways depending on your calculator. Now, as soon as I hit graph, it's going to graph this, and it's really, really painfully slow. So it's redrawing my original cubic. That's fairly quick. And then when it draws the n-deriv, the reason it's so slow is because it's basically doing all of those symmetric difference quotients. It's like actually plugging points in and plotting them. So it's super, super, super slow. I thought about doing a cut on this and showing, and having it magically appear, but I actually decided to leave it so you can see how truly slow it is. But as it draws, we can notice a few things. So at -1, where we knew the graph was flat, look at my derivative graph, it passes the x-axis, it's 0. When x is 3, the same thing. In between, I have negative slopes, so I have negative plotted derivative. And then on the sides, I have uphill slopes, so it's positive slopes, that's why I have those positives on the outsides. Now notice this. My original function was cubic. My new function, it really looks like a quadratic, doesn't it? And that's because it is. We will learn about why that happens a bit later, but I want you to notice it. As you're doing these, try to pay attention to what's my original function and what does my derivative look like? Because that can be super helpful. Recapping again, just to show this really quickly. To get this on your calculator, it's math 8 to get the n-deriv. Depending on your calculator, it's going to look like one of those two things. The comma that you need is above the 7, and then vars, yvars function to get the y1, or alpha trace to get the y1. This is newer calculator, older calculator. But that is how we can draw a derivative graph on our calculator. And by the way, it's important to know about the symmetric difference quotient, because if the original function has a corner or a cusp, the derivative isn't defined at that spot because you can't draw a tangent line on a pointy bit. Our calculator will do a symmetric difference quotient and actually give you a value for the derivative on a corner when we actually know that's not the case. So that's why we need to know why or how our calculator is programmed so we can know how it's going to mess things up. Like if I graph the absolute value of x, here's my absolute value. I have a slope of -1 on the left, +1 on the right. In between, at the origin, my slope is actually not defined there. But my calculator is going to tell me that the value of my derivative at 0, like if I hit trace and go down to my y4, it tells me my slope is 0, and that's because of that symmetric difference quotient. It's going to each side of the 0, 0, and finding the slope, which is going to be a 0. So we have to know about how the calculator is programmed so we can know why it's wrong, or if it's wrong, rather. It's generally right, though. And now you have a new calculator trick.